But what it also tells us is something very important about science, and that is it is fundamentally a conservative intellectual enterprise. Science wants to have an agreement over as big a field of inquiry as possible, but it is not always clear where a new discovery fits into this picture. And so that's what, to me, that is what makes the history of science interesting, is how um, is how new ideas get accepted or don't.
Today I'm here with Dr. Richard Haglund at Vanderbilt University. Dr. Haglund, how is your day going?
It's been very busy. We're getting ready to move much of our laboratory from one building to another, and we have very large optical tables, 5 feet by 12 feet by 2 feet thick, that weigh a ton and have to be moved out through a window in the building by a crane. And there are 4 of them to be moved. So
that sounds a lot of work.
It's exciting.
It's exciting. Could you tell the audience more about your background, your research, and who you are, like in
Sure.
deep personal level?
So I grew up in Iowa, in a relatively small city that had a superb school system, which was very fortunate. I went to Wesleyan University in Connecticut as an undergraduate and began graduate studies at the State University of New York at Stony Brook. And at the end of my first year, 2 very important things happened. One is that my wife, of now over half a century, said yes to a proposal of marriage. And then the next week, I got a notice that I was going to be drafted into the Army. This was during the Vietnam era.
Wait, how old were you when this happened?
I was 26.
Okay.
And my wife's friends all said, well, you'll have to postpone the wedding, to which her response was, we have 6 weeks, we can get this done. And we did, but I spent the next 3 years not in graduate school as I expected, but in the military. Fortunately, I ended up spending all of my time in the United States. When I got done, I was ready to go back to graduate school because I had a Danforth fellowship. I could go wherever I wanted to. And I had gotten some new ideas about things that I wanted to do for graduate work. And it turned out one of the best places to do that was the University of North Carolina in Chapel Hill. And so we spent the next 4 years in Chapel Hill. From there, I took a postdoc at the Los Alamos National Laboratory, which then turned into a permanent staff position there. It may be interesting to your viewers to know that I did my PhD in experimental nuclear physics. After a year as a postdoc doing more of that, I decided that I didn't want to do that when I grow up. And I had the opportunity to join a laser physics group that was building very large laser systems for laser fusion experiments. Although I had always wanted to have a career at the university, when I got out of graduate school, that was a terrible idea. The universities were not appointing new faculty. And so the time at Los Alamos, almost 10 years, was a time that I think I grew a lot professionally. I learned a lot of things that they don't teach you in graduate school. And so when the time came when universities were beginning to appoint new faculty, I was ready to go. And so when I came here, it represented finally what I kind of envisioned that I wanted to do back when I was even in secondary school. But it took a while to get there.
Wait, you said you were in military for 3 years?
Yes.
And by the time you're back, you were 29? when you started your grad school?
Yes,
And
and I worried that and fretted somewhat that I was getting very old. I thought. I have the next younger member of the family I grew up in, my sister Elizabeth, and I, who were always very close. And I once said to her I was worried about being old before I even start. And she said, you know, by the time you're 40, it probably won't make any difference. And that turned out to be very good advice. By the time I was 40, I was pretty much in the same place as all of my friends who had not been delayed with their graduate school because of military service or other things.
and what made you decide that you want to study physics?
That was not a decision I came to easily. I I had really wanted to be in the academy, so to speak, but I had very significant interests in history and in literature, and I wasn't sure which of those things I really wanted to do. In the beginning of my junior year, um, I thought I needed to make a decision, and I thought long and hard about it. Um, and I had almost committed myself to changing my proposed major from physics to history. I had a favorite history professor who was on leave from Wesleyan that year, and I wrote him a note about the decision I was thinking of making, expecting to hear from him. Um, um, Go ahead, sounds like a great idea, that sort of thing. Um, and instead, I got back a 3-page typewritten letter from him. Interestingly, in those days before mail got very, very slow, I mailed the letter to him in London and got back a reply 9 days later.
Wait, is that fast or slow?
That's which is fast compared to
Compared to-
today, where it would take 2 weeks.
Oh, okay.
In any case, Professor Toshiro said not one word about, oh, yes, you should, or yes, this is a wonderful idea, or no, maybe you shouldn't. He wrote for 3 pages a very reasoned, nuanced discussion of which formal studies, in the sense of coursework and formal PhD training, which things can be put off with the least loss. And he said, for someone like you who has very diverse interests, this is really the critical thing you have to decide. It's not should I do A or B, it's which parts of A or B do I have to do now. I thought about that letter for about 24 hours and realized if I left physics then, I would never be able to get back because I was at such a hinge point in the training. And I realized that if I completed my graduate education in physics, that I could probably find ways to go back to cultivate my interests in history. Now, that does not by any means suggest that history is easier than physics. History is extremely difficult in very complicated ways. There are different styles of inquiry, and the subject is human beings, which are very complicated compared to the behavior of electrons. But I realized that Professor Toshiro was right, and that if I was going to do physics, I needed to focus on that for the years immediately ahead, which I then did, except for that diversion into the military. Uh, and so by the time I finished my degree, I was really very focused on physics. I continued to an amateur interest, especially in the history of science. Now, when I came to Vanderbilt and was asked what I would like to teach, I mentioned to the department chair that I would like to teach occasionally a course in history. And he wrinkled his nose and said, "Well, maybe not so fast. Wait until you are tenured. And then you can teach what you want to, and what your colleagues think of this strange interest won't matter to you." And that is in fact turned out to be the case, so that I have, over the time that I've been at Vanderbilt, taught courses in areas that interest me, not only having to do with the history of science, but also with interesting people who had careers at the intersection between science and literature, like Johann Wolfgang von Goethe, the great German poet, and also more recently courses on science, politics, and economic growth, and the way those intersect and interfere sometimes with one another.
What drew you into history? What specific aspects of history were
Oh,
you interested in?
because people are endlessly interesting, and the things they do are sometimes puzzling, sometimes inspiring, uh, almost always intriguing, in the sense that you learn from history how they make their decisions and how they go about things. So, for example, if you were to study the history of premature discoveries in science, this is an area that I've been interested in off and on. There is a famous case in the history of British physics of a young man named James Waterston, who invented the kinetic theory of gases 20 years before Sir James Jeans, who is widely known in the history of science as the one who did this. Well, Waterston's paper was turned down by the Royal Society. It was not published. He was, of course, not happy with this decision, basically decided to give up on physics, went off and invented industrial group accident insurance at the beginning of the Industrial Revolution, which made him a very, very wealthy man. Years later, when he was already a sitting member of the House of Lords, Lord Rayleigh discovered his correspondence in this rejected paper, and he immediately recognized Waterston's name. And he wrote him an interesting note. He said he was really sorry that his colleagues had not had enough vision and perspective to accept this groundbreaking discovery. But he said that it is important for a young person to establish themselves in science first with something that can be easily judged by their peers. And then, if you want to start a revolution, it's okay to go ahead and do that. And the reason why I think these kinds of things are interesting is that they show, first of all, the human side. The human side of history is filled with triumphs and tragedies, excitement and disappointment, all the things that make human life variegated and interesting. But what it also tells us is something very important about science, and that is it is fundamentally a conservative intellectual enterprise. Science wants to have an agreement over as big a field of inquiry as possible, but it is not always clear where a new discovery fits into this picture. And so that's what, to me, that is what makes the history of science interesting, is how new ideas get accepted or don't. In our initial discussion, you referred to a famous quotation from Max Planck, where he says that you really can't get new ideas accepted in physics until the people who are the champions of the old ideas are dead, or words to that effect.
Yeah, I do have the quote. Max Planck said, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that and a new generation grows up that is familiar with it. So that sounds
Well,
like
but even though Max Planck knew that,
uh,
when Einstein comes along in 1917 with his papers on the photoelectric effect and general relativity, when 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 Planck nominates Einstein for membership in the Prussian Academy of Sciences, in his nominating speech, he says that he's proposing that he be made a member of this honorary academy because of his work in relativity. And then he says something roughly like this: we won't hold Einstein's youthful indiscretion about the light quantum against him. Everybody makes mistakes when they're young and enthusiastic. And so Planck himself fell into this. And we know from Einstein's history that he also basically never really accepted quantum mechanics as it came to be understood in the community, because he didn't think quantum mechanics, with its probabilistic view of reality, could really be true. Because Einstein was what we would call a philosophical realist. He believed that you had to be able to say it is this or that, not that it's a linear superposition of probabilities that it could be this or that, which is still the quantum mechanical view.
when someone comes up with these theories, I guess like someone has to establish their credentials in the field already. But that was not the case with the Einstein, right? When he came up with special theory of relativity, like he was very young and was not that renowned in the field.
Well, that is kind of that's kind of what people believe. It's not clear that that is really that really accords with the facts. Einstein was recognized very early on as a very great talent. He had rather unorthodox ideas for the time, and the thing that's important to realize about Einstein is that he believed it was really important that he be true to himself and to his vision of what was important. And yet, more recent scholarship suggests that one reason why Einstein's 1905 papers, the famous trio, actually found quite ready acceptance was because Einstein drew on threads of thinking that had already existed in late 19th century physics and that were recognized as serious problems waiting to be solved. Special relativity is one of the obvious examples of that. There had been experiments. Lorentz had proposed a version of relativity theory, and so the ideas were floating in the air. And what Einstein's genius was at least in part his ability to pull those threads together and to make a coherent story out of them that people were able to then accept pretty readily.
Hold on, what was Lorentz theory? What was his idea behind anything related to
Well, he had the
relativity?
idea of relativistic contraction of length and relativistic dilation of time. What he did not have was a formulation that would make it readily apparent that this could be correct and that you could measure it.
Mm.
And that's what Einstein did, was to help people realize that the um, that the special theory of relativity, as he developed it, had measurable consequences. Interestingly, by the way, the French mathematician Henri Poincaré was only about 2 months behind Einstein with a special theory of relativity that looked very much like the one that Einstein published.
When you mentioned earlier the trio he published in 1905,
Yes.
first one was special relativity.
So there's special relativity, there's the light quantum,
Mhm.
and there is the diffusion equation,
Mhm.
and developing the quantum mechanical basis for understanding Brownian motion.
The second one is photoelectric effect, right?
It's not really the photoelectric effect, although that is one. The Einstein paper, which is about the light quantum, is very interesting because what it starts off by asking is, we know, he basically says, we know from Maxwell's theory that at great distances from atoms, light behaves as if it were a wave. But we know from the behavior uh, of atoms, and we didn't know very much in 1905, but he said we do know that that light begins somehow with the excitation of atoms. And so what he asks himself is, how do we get from a length scale that is atomic to a length scale that is macroscopic, where the nature of the physics seems to change so radically? So in that paper, what he does is he poses this question, and then he gives a whole bunch of examples that show how you might understand that, one of which is the photoelectric effect. And that's why everybody calls it the photoelectric effect paper. But that's not what the paper was really about. It was about this puzzle.
I see. What do you think with Einstein? What do you think was the reason he came up with all these theories? Was it his pure genius, or was it something else that we don't know normally?
There have been a lot of studies about this, but I think from the reading that I've done by historians of science and by physicists who've written widely about the history of science, and particularly about Einstein, one of the more famous ones being Gerald Holton from Harvard. And what they notice about Einstein's way of going about problem solving is, first of all, he's very concerned about measurement. How do you know things? Because of the way you choose to measure them. And the other thing that's very characteristic of his thinking is that he looks at problems that occur at the interfaces between the classical disciplines of electricity and magnetism, thermodynamics, and mechanics. So, for instance, the theory of relativity arises at the interface between mechanics and electricity and magnetism, because how does he formulate the problem? How do I measure the physics of an observer who's moving at very high velocity? And the way he does it is by his famous thought experiment with the light clock.
Yeah, he's moving in a train, and then there are
Yes.
two observers or two clocks that is observing some lightning.
Yes, and he was really very concerned about how measurement itself teaches you about underlying reality. And even in later life, where he found himself very much in opposition to what we view as the modern formulation of quantum physics, he couches his objections in terms of an experiment, the so-called Einstein-Podolsky-Rosen experiment. And so he is a theoretician who is not simply entranced by the mathematics, beautiful as it is, but who is very concerned about how you actually go about measuring things.
Wait, can you explain more about the Einstein-Rosen-Podolsky thing? More?
I'm not the right guy to ask about that. It's basically the experiment in which he undertakes to show that it is not possible for a quantum state to be only a probabilistic entity, and that the act of measurement itself causes the quantum mechanical system to be in a particular state which you can measure, not to be with a 50% probability to be in either of two states. So kind of the in a sense, he is taking the Schrodinger cat experiment to its extreme. Uh, the, the 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 final blow, in a way, for uh, um, the Einstein, for the EPR experiment comes with the work of the great theoretician John Bell later, and um, I just don't feel that I'm qualified or have a good enough grasp on it to put it in simple words.
That's a good explanation.
Yeah.
So with Einstein and Newton, people say that Newton was a pure genius because he had to develop his own tools to explain the theory of gravity. But with Einstein, there were so many tools already developed with the tensors like and everything. So how would you compare their genius? I know, I mean, they both are genius, but how would you compare their genius?
I don't like those kinds of comparisons. I have to say, frankly, I think um, what they what by trying to put things in some kind of ranking, what you're ignoring is the fact that genius comes in different kinds of packages. Einstein's greatness, in my view, is first of all his understanding of the role of the relationship between theory and experiment. Second, his ability to look at problems at the interfaces that seem to combine aspects of one important part of physics with another. And the third thing is his ability to adapt tools that are already there to new problems. In my mind, you see that most clearly in his development of the general theory of relativity, which is all by himself. There's nobody else out there thinking about the idea of curved space time and with time on an equal coordinate footing with the spatial coordinates. Um, Now, I'm prejudiced in the sense that I did my undergraduate honors thesis on general relativity, um, and was fortunate enough to work with someone who was a real expert in it. Um, and what I learned is that in Einstein's general relativity papers, um, you see three very interesting aspects of his thought. The first is that the first two or three pages of the paper have no mathematics in them at all. Um, uh, they describe in very beautiful, articulate, fantastically literate German, actually, why it is reasonable that space and time should be treated on an equal footing. Now, remember, this is 10 years after special relativity, and he's been thinking about this for a long time. And then he develops the theory, and at the end of the paper, there's like a 3 or 4 page appendix, which is basically everything you need to know about Riemannian geometry and we're afraid to ask, where he takes the tools that Riemann had invented in differential geometry and applies them to the physics problem of how do you describe space-time in a curved geometry.
Wow.
And then, by the way, as you know, his reputation was made because he made a specific measurable prediction, which is that starlight would bend in the gravitational field of something heavy. And Sir Arthur Eddington, the great English astrophysicist, took him up on it, and they did the famous expedition to Africa to observe the bending of starlight around the sun during a solar eclipse, when they could block out the sun's light and just measure what was coming from distant stars and bending around the sun. But Einstein was also someone who, rather like Dirac, believed that when you got things right, they were really beautiful, and that there was something that was so fundamental about that and so beautiful that you could predict something as exotic as the bending of starlight with your theory. Um, I have to believe that he must have had the similar confidence that Dirac expressed later, which you point to, uh, where Dirac says it's more important to have beauty in your equations than it is to have them be correctly fitting the data that are known, because he says when you finally get around to it, it will turn out that the beautiful stuff is what really works. And I can tell you from having played with this as an undergraduate already, that there is a striking beauty in the way that general relativity just puts time and space on an equal footing and allows you to formulate all of the um, all of the basic um, equations of physics, including, say, Maxwell's equations, in the same kind of tensor calculus formulation that he uses for general relativity. If you think about the four Maxwell equations that you've learned, it's a one liner in
Yep.
this representation of the tensor calculus. And that is likewise the same beauty of the Einstein formulation. The other thing is important, and that is his idea that you can define a metric on the space of possible experiments in general relativity, and that, as elsewhere in physics, that the real physical solution is found at the extreme values for the metric. And that's a really beautiful, deep concept that you find everywhere else in physics.
Why do you think all these beautiful equations do even exist? Is it because nature is simple, or do you think that nature is beautiful itself?
Nature is not only simple and it is not only beautiful, but more important than that, nature is elegant in the full aesthetic sense of that word.
Wow. Do you think, what do you think is the most beautiful equation that heartbreakingly failed?
Oh, that's an interesting question. There are a number of examples, of course, of theories that people thought were beautiful and that turned out to fail. I don't know of a good example of an equation that people thought was interesting and might fail. But I have to say that my idea that the universe is elegant comes from Brian Greene's book of the same title, The Elegant Universe, which is about string theory and the elegance of the theory that we cannot yet verify because we cannot measure at the length and timescales that would be required. But there is a beauty in in the simplicity of the universe, and there's a simplicity in the beauty of the universe. So there's kind of a symmetry there. It is a sort of symmetry that was captured by the German mathematician Emmy Noether in Noether's theorem, which is that every conservation law in physics is associated with the mathematical symmetry in the equations of physics. That's just a fantastic idea that is simple and beautiful in every respect.
Wow.
I mean, it's one reason why I think science at its deepest level is not always easy for people who are not scientists to understand, because it relies to some extent on having enough background to look at the geodesics in space time and say, yeah, this is Riemann geometry. The other question that it raises, of course, is why is it that when physicists get around to trying to find an elegant theory, the mathematics they need is already there? somebody discovered it 50 years before the physicists needed it. This is true of Hamilton's quaternions, for example, which have a way of turning up in the Hamiltonian version of quantum mechanics.
Maybe mathematicians are way more advanced than physicists.
One of my dearest friends, who is a mathematician, would be happy to sign on to that view. He says we're just kind of several steps behind in physics.
Or maybe physics is just applied math.
Yeah. Well, that's a little that's a pretty strong statement. I guess I'm not sure I'd subscribe to
that. With the way physics is done these days, it is definitely different than the way it was done during the golden era of physics, when everyone was coming up with their own theories, and there was, I guess, very little collaboration between physicists. So how do you think the physics culture is going to change? Or, I mean, it has already changed into like huge collaborations.
Yeah, that's a very interesting question. In some ways, physics is already bifurcated into big physics and little physics. So the big physics that's done at places like CERN, at the major observatories, for example, they do projects that take decades to come to fruition and rely on the most advanced technologies that we can think of. And then there are things that are done in individual laboratories. I view that as being a kind of natural evolution. The fact that physics nowadays is often connected with other disciplines. So the physics of things that are alive is the subject of biological physics, or it is one of the subjects of biological physics. I think that the kind of interconnection between disciplines is partly a natural evolution. This is true. Excuse me. This is true in history, for example. Historians start off looking at the chronology of how things happen, and then they start looking at the people, and they think about the ways in which the differences between individuals affect the course of history. And then somebody comes along and says, oh yeah, but you have to recognize that part of these historical developments were shaped by economics at the time. And you find historians, some of whom start to plant a foot in economics and discover that that's interesting. And so, to some extent, I think it's a question of expanding horizons. The more you think about your own approach to the scholarly problems that you're interested in, the more you realize that many of them are related to work that is done by other people. When I was an undergraduate, people thought of optics as a part of physics that was pretty much separate from condensed matter physics.
Mm-hmm.
Once the laser was invented, people had to start thinking about the ways that laser light interacts with matter, because at its higher intensity, the interaction of light is no longer simply categorized as light goes through material and it bends according to the index of refraction, or it is either transmitted or reflected or partly absorbed. Now you discover that things like the index of refraction that describes the refractive power of light actually depend on laser intensity, so that you can have, for example, what's called self-focusing, where a light beam is so intense that the light itself causes the focal properties of the material to change. And this is in its way, is kind of a natural evolution that comes from the fact that you have new instruments, new ways of measuring. I think that the evolution of computing power has had a similar effect. We can do experiments now that you couldn't conceive of doing
Mm.
30 years ago.
How was optics back then when it was completely disassociated with the molecular like material science?
Well, there you had basically two kinds of materials: insulators and metals. Metals were perfectly reflective, very highly conductive electrically. Insulators were transparent and did not conduct electricity. Well, the materials that we've been fascinated with for a quarter century, vanadium dioxide, is somewhere in between. It's not a very good insulator, but it does transmit light. It's not a great conductor. It's not as good as copper, but it's better than silicon. And so, in as people have opened their eyes to the existence of this different class of what are called correlated electron materials, they discover that there's this intermediate regime that has very interesting properties. For example, it can be made to transition from insulating to metallic behavior and back again. And so I think a lot of what we see as increasing complexity, for example, is just a natural evolution of discovering that the world is not as simple as insulators and metals. There are these semiconductors in between that have very strange properties, and without which, in particular in the case of silicon, without which our current civilization would not exist in its present form.
Wow. Do you think there will come a point where we need to go back to our existing frameworks and theories and fix something fundamentally from the scratch? For example, quantum mechanics itself. Maybe it is not truly undeterministic, and maybe we need a realist theory to determine or to define all these existing quantum mechanical frameworks.
Yes. Now, that I'm sure we will. You already are familiar, I think, with one example of that. Everybody knows that there are serious problems with the so-called Standard Model, which describes the nature and interactions of the elementary particles. We know there are problems with this theory, and people are working very hard on that. New solutions have been proposed. The important one that I am aware of in the elementary particle area is supersymmetry. Well, we can't find any experimental evidence for it. And so now the question is the theory wrong, or is our capacity to measure not sufficiently sophisticated? Where's the problem? So I think it is natural always to wonder about those things. One of the things that strikes me when um, when scientists talk about the indeterminacy of quantum mechanics is, yeah, but remember how that indeterminacy is phrased. The indeterminacy is phrased as a product that the uncertainty in length times the uncertainty in momentum is on the order of Planck's constant. Planck's constant is a very tiny number, 10 to the minus 34. Okay? If I imagine that delta x and delta p are roughly about the same size, 10 to the minus 17 times 10 to the minus 17 is about the minimum uncertainty. Well, we can't measure much of anything to better than about 10 to, apart in 10 to the 12th. And that means that if I look at an electron microscope picture, I can tell you this is a gallium atom and next to it is an arsenic atom, and vice versa, and they are arranged in this and this kind of a lattice. And I can be pretty darn sure that that is exactly what the real picture looks like. And so we have to be very careful about taking concepts like uncertainty, which is by itself a little vague. First of all, it's generally regarded as a mistranslation from Heisenberg's word, which means literally indeterminacy. But our ability to measure things has gotten incredibly good since Heisenberg's day, and we are getting very close to limits where we can say, all right, maybe theoretically there is some uncertainty here, but I can look at that electron microscope picture and I can tell you these are atoms of species A and these are species B. And I can be very certain that that's what they are.
My understanding of uncertainty comes from the fact that when we are trying to observe something, we have to send in some form of um, electromagnetic wave, and when it interacts with the particle itself, it just accelerates the particle, and we don't really know like where it is going to be. Is that the correct understanding?
Yeah, I mean, that's basically the Bohr microscope idea. You send light in, it gets absorbed, that gives a quantum of energy to the particle and changes its momentum.
Hmm.
But again, people keep finding interesting ways to actually measure. I read just today a report of a study of erbium ions inside yttrium oxides, where the researchers have figured out a way to measure the individual spins of the 5 yttrium atoms that surround the one erbium dopant that is sitting in the middle. Now you're talking about us saying this atom has a spin that's oriented this way and its neighbor has a spin that's oriented in the opposite direction, and I can measure that.
And how does that change anything?
What that does is tell you that I can measure the quantum mechanical properties of individual atoms in a solid.
Oh, wow. And we didn't really need to send in any extra like external electromagnetic waves for
No,
that?
it is a microscope type measurement. It's a microscope that has a cavity in it that enhances the interaction of the light with the spins in the oxide.
Oh, wow. And does that change anything with like how precisely we can measure things?
I don't know. I hope it keeps some theorists awake at night. They should be thinking about things like this.
Wow, that's interesting.
And this, so I mean, this comes back to your question of why I like to do physics. I think that one of the very interesting things about physics, that's a little different from, say, biology, is that the interplay between theory and experiment can be so close in physics. Not because we're so great at doing really complicated things, but we are really good at doing some simple things really, really well. It has been said, and I subscribe to this, that physicists really only understand 2 things in this world. One is the hydrogen atom, the other is the harmonic oscillator. But we understand those with a precision that is just almost astounding to think about. And the fact that we can do it so precisely is what gives us the ability to really have strong predictive power over what happens. The people who do strong interaction physics, so with much more energetic quanta and much more complicated structures, quarks and gluons, they have it's the same thing. They are becoming more and more precise in their capabilities of measurement. In their case, one of the challenges is that seems to require the construction of ever larger machines that take longer and longer to unravel the mysteries behind these very rare processes that they want to see. But I don't see anything in the history of physics that says that this is an enterprise that is foredoomed to failure. I think that it's going to be figured out.
Yeah, with the recent developments in quantum information science and the new promises that quantum computing brings in, how do you think the field is going to change, the field of quantum information science? I mean, the growth has been pretty much exponential, with quantum mechanics being formulated around like 1930s to 40s, around that
Yeah,
time.
really
Yeah,
the 1920s
20s.
and
Yeah,
30s. Yeah.
yeah, and we already have quantum computers that are up to 100 something qubits. And how do you think, or how do you see the future of quantum information science?
I wouldn't dare predict anything about it. I think it's going to be a wild ride.
Mm.
And I think one of the reasons for it is we're still not sure whether quantum computing is a general all-purpose tool like von Neumann computing has turned out to be, or whether it really opens something that is fundamentally new. And one of the ways you see that is in the back and forth between Google, for example, and IBM, where Google says we've just shown quantum supremacy on this problem. And a week later, IBM comes back and says, oh, actually, we did this in 2 days on a regular old computer. Well, now the regular old computer is an exceedingly powerful machine. And I think it's going to be really hard for a while to separate the public relations of quantum information, the hype, if you will, uh, from what is actually going to be truly change, what is really going to change the world in our views in quantum information systems. But I think that's part of the excitement, is trying to figure out how far we're going to be able to push it. Right now, we're up to 100 qubits. Well, most people say that you probably need something closer to 10,000 qubits to really do a serious quantum simulation of a realistic system. Let's assume for the moment that that estimate is reasonably true. Well, we've got orders of magnitude improvement ahead of us. Um, and we'll see whether our control of trapped ions, for example, is good enough that we can put 10,000 of them in an array, 100 by 100 array. As a laser guy, I'm sort of partial to the idea that you might as well compute with photons. They're cold, they have easily identifiable states, and you can pipe them around through optical fibers. Who knows?
The whole idea of quantum mechanics is that it is in a pure fundamental level of atoms and molecules. Things are very
and things smaller.
And things smaller. Things are purely undeterministic. So, do you think it is a good approach to even try to come up with algorithms that are deterministic in nature to solve problems?
If remember what I said about the limits that are imposed by the uncertainty principle, they're not absolute. That is, Heisenberg does not say that you absolutely can't measure this quantity to an arbitrary degree of precision. There's a trade-off. And we already know that from the study of things like squeezed states in light, that you can squeeze one quantum variable at the expense of the other and reduce the uncertainty. So I think one of the important things that needs to happen is that our discussion of the meaning of quantum physics itself needs to be more sophisticated, and we need to be a little more careful in defining what we mean by indeterminacy, for example. And we need to constantly be thinking in terms of quantities and in terms of measurement schemes. Because at bottom, what makes physics is this very close coupling between the theories that we put together of the universe and our ability to undergird those theories with critical measurements that give us confidence that the theories are correct. And of course, then there's always the nod to the ineffable qualities like the aesthetic beauty and symmetry of the way we do our explanations. It remains a fact, interestingly, that the precision with which the universal gravitational constant is known is less than the precision with which the spin g factor of the electron is known, by
Wow.
orders of magnitude. That's a fact that might surprise you, but it happens to be the case.
Wow.
So that the precision with which what indeterminacy has driven us to do is to get really, really good at certain kinds of measurement schemes.
What's your favorite theory so far?
My favorite theory, um, well, in some sense, professionally, I would have to say quantum electrodynamics, which is the theory of electromagnetism. But uh, I like I I am enchanted by condensed matter theory. It's messy.
Mhm.
It's very approximate, but its ambition is boundless, and it's done pretty well for us. Um, if you ask me what theory do I find the most aesthetically attractive, I'd have to say general relativity. I've never really gotten over my fascination with that, even though it's not what I do professionally. Uh, I just think it is so elegant, and it is so clearly a product of a of a remarkable mind and remarkable minds at work, that you can clearly trace. It's the theories of condensed matter are messier in the sense that they're approximate, and uh, they're always on the edge of working or not working. Um, but I think the especially now that we have measurable evidence for gravitational waves, the general theory of relativity has been verified in ways that are far more universal, if you like, than the original measurement of light deflection around the the uh, the light deflection during the eclipse of the sun.
Wow. One completely off-topic question. When you were in military, were you still doing physics? Because the reason I'm asking this is like I know Schwarzschild, who was in military when he came up with this entire Schwarzschild metric that describes the event horizon on a black hole with this beautiful, elegant mathematics.
Mm-hmm.
And I'm just curious, like, how was it
I
being in the
spent I
military?
spent last year in a little nuclear physics laboratory, and it was in. I can't say that I came up with anything like the Schwarzschild metric, but it was in that laboratory that my early interest in nuclear physics as a subject for graduate work was formed. Um, so yes, I did have opportunities there. I was very fortunate in that regard.
Mhm. Who would you say was the most influential physicist for you personally?
I would say, actually, I would name two people, and they were both my advisors. One was my undergraduate advisor, who was a very important figure in numerical schemes for evaluating general relativity back when before supercomputers, when you really had to be really, really good at numerical analysis to do things that were solvable on the primitive computers that were available then. Um, and what I valued about Richard Lindquist was that he was he was in my mind the ideal of someone who was deeply connected with this beautiful symmetrical part of physics, general relativity. And he was himself also a very fine musician. And so, in some ways, he represented to me the ideal of a person who has a very rich, full life that goes beyond physics. I remember walking by his house on afternoons every now and again and hearing him play the newest Beethoven sonata he had decided to tackle. And that was very inspiring. My graduate advisor was a very different kind of person. He was a very, um, I've often said that Thomas Clegg was a kind of nuts and bolts experimentalist who was really hands on and so on. And from Tom, I learned to value the deep, intimate, almost personal acquaintance with the hardware if you're an experimentalist. And those two, in terms of the academic side of my career, really were kind of two different poles of the way they viewed science and the role that science played for them. So it was wonderfully important to me to have had the exposure to both those kinds of both those ways of approaching physics in a professional way.
In last 4 decades, you have contributed so much in the quantum information science realm. What is the proudest contribution you have made personally?
Well, I have not really done much in quantum information. That's relatively new in our group. This is something that started about 6 years ago with a student, Matthew Feldman, who is now on the staff at the Oak Ridge National Laboratory. So, in terms of quantum information, what I've been focused on is room temperature, the development of room temperature qubits in hexagonal boron nitride, which is a wide bandgap insulator where you can excite qubits optically. And I really am enjoying that work. That is continuing. Who knows where it will lead? We do not yet know whether we're going to be able to do room temperature quantum computing because the leading candidates right now have to be done cold, that is, liquid helium temperatures. But on the other hand, if you think about it, how are we going to deal with the information that comes from quantum computations? They're going to go through room temperature silicon.
Yes.
And so the question of whether or not it's going to be possible with all of the fluctuations, the thermal fluctuations that happen at room temperature, whether it would be possible to have well-defined quantum states that can be used for computation, that's an open question. We see single photons that we can capture from hexagonal boron nitride. The next phase of our work and the proposals that I have made in conjunction with colleagues in electrical and mechanical engineering is to see if we can coax correlated photon pairs out of HBN.
That's interesting.
At room temperature. So that's the next odyssey, and you know the whole point of research is if you can answer the question already, then it isn't research. So this is where I'm headed in that field at the moment.
I also saw this picture on the physics department website that John Jumper also worked in your lab at some point, who ended up being Nobel laureate last year.
Yes.
So
yes.
How was that experience? How many years ago was that?
John was a typical enthusiastic, very gifted experimentalist. He was only in the lab for a semester, I think, and then he moved on to a different lab. I'm flattered by the association that some people have made, but I cannot claim to have had any definitive influence on him. It's exciting for Vanderbilt to have had someone from here who has reached that very important marker of scientific achievement, and it's great fun to watch and have some association with it.
Do you have anything to say to the students or any viewers who are interested in physics and science in general?
Yeah, read more history of science.
Just that?
Yeah, because and the reason for it is because the history is both, um, in some cases, it's a warning. So I first learned the story of James Waterston and his attempt to formulate and publish the kinetic theory of gases before the community was ready for it. I read about it in a very famous paper by Steve Brush, a statistical physicist at Maryland, called "Should the History of Science Be Rated X?" And his answer is yes, it should be, because if students read this, they're going to be very discouraged. On the other hand, if you read the stories of Einstein's route to the formulation of any of his three 1905 papers, or if you read the way Paul Dirac found his way to the relativistically correct version of quantum physics, which also just incidentally happened to predict the existence of antimatter, which people thought was totally nuts at the time. That's really inspiring. This is somebody who is driven by this vision of physics as the most beautiful economical expression of truth, formulated in elegant mathematical form. So reading about the way people came to those discoveries, I find very inspiring and encouraging. It says that humans can actually do this.
Is there any theory in physics that you wish to be true?
That I wish to be true.
Yeah. Besides string theory, I know it's a very complex theory.
That's a really very interesting question. No, I don't have a wish that this theory or that theory would be true. I would love to see if we could get to a point where condensed matter theory would look a little less like computational physics and more the expression of something as simple and elegant as quantum electrodynamics is. I don't know that that's possible. I just think that it is, in some sense, intellectually awe-inspiring to look at the way physics has managed to wrestle the untidy, messy nature that we see outside into a form where we can understand things as complicated as the physics of living biological systems. On the one hand, an astrophysics at a completely different length and time scale, and a very different energy scale. It's just interesting to be able to be part of an enterprise that, as one definition puts it, has as its goal the explanation of the interactions of matter and energy at all lengths and time scales. And maybe that's a fitting way to summarize my feelings about physics. That's a wonderful, ambitious, unreachable goal that can get you out of bed every morning and into the lab.
If you're not a physicist or a historian, how would you see yourself in a different career?
There was a time when I imagined myself as a concert pianist.
Do you play piano?
I was pretty good. Oh, yes. I had a very nice fling at that when I was an undergraduate, but that was in a universe where, by rule, Wesleyan students could only take 4 courses. They didn't load up on hours as today's undergraduates do, and so I had time to spend.
A very emotional question. Do you have any regrets? Any career choices you made or anything you did?
Oh, no.
No?
Not even turning down Harvard to go to Wesleyan. Wesleyan was a wonderful place for me.
You got into Harvard, but then
I got into Harvard twice and didn't go to Harvard.
Why?
For various reasons. And the case as an undergraduate, I did some research on the faculty at both places, helped by an uncle who was an academic, and concluded that academically I was at least as well off at Wesleyan at the time. Um, by the time when I applied to graduate schools, Harvard was one of several I applied to, and it happened that in some respects, both Cornell and Stony Brook looked better to me, and for personal reasons, I ended up choosing Stony Brook.
Well, thank you. I have one more question. This looks pretty interesting. Could you explain what this is?
Yes. So this is a block of pure fused silica that was given to me by a friend at the Helmholtz Institute in Germany. If you look at the front of this, you will see a very tiny hole that was made by the beam from a particle accelerator going into it. And then what you see, this beautiful leafy pattern, is the fractal pattern of damage that is left in the solid as the ion beam comes to rest. And basically those tracks are formed by energetic electrons that damage the material and make it opaque so that you can see this tree structure. Now, you know what a fractal is, right? It's a self-similar structure at every length scale. And the ion tracks in solids are one of the beautiful examples of fractal geometry.
I know the Mandelbrot fractals.
These are the Mandelbrot fractals.
How do you say that? Mandelbrot?
Mandelbrot.
Mandelbrot, yeah. Yep.